Hey everybody, Matt Morgan here. In this lesson, we're going to talk about properties of light from section 6.1 in the OpenStax textbook. In this lesson, we'll talk about the electromagnetic spectrum, properties of waves, how light behaves both as a wave and a particle, and we'll be able to work homework problem number 7. So what do all the following have in common? They seem completely different. Visible light, infrared, ultraviolet light, microwaves, radio waves, cosmic waves, all of those. How are they the same? Well, it turns out that they are all part of the electromagnetic spectrum. They're all made of the same stuff. Let's look at figure 6.3 from the textbook. We see from cosmic rays with very, very short wavelengths all the way to radio waves with wavelengths longer than a football field. The visible spectrum, the amount of electromagnetic radiation that we can detect with our eyes, is a very small part of all of the electromagnetic spectrum. There's so much more than what we can just see. So that figure shows light behaving as a wave, and for the most part it does. Let's explore that. What is a wave? It's a term we use every day, but it is not a trivial question. A wave is a regularly repeating transfer of energy. One of the most simple waves you can think of, not water waves yet, we'll get to that, is waving your hand. That is a repeating transfer of energy. There's water waves. That is another kind of wave. So regularly repeating energy, they usually occur in some type of medium, although electromagnetic radiation doesn't need that. All waves, including light, have both a wavelength and a frequency. Note that a shorter wavelength results in more waves per unit time. Now this relationship only works if all light travels at the same speed. And does it? Yes, in a vacuum, all electromagnetic radiation does travel at the same speed. That speed is about 3 times 10 to the 8 meters per second, the speed of light. With this constant speed, how are the wavelength and frequency related? Let's look at that. It turns out that wavelength and frequency are inversely proportional. That's because the speed of light is constant. There's the value we saw in the previous slide. Wavelength is in units of meters, denoted by the Greek letter lambda. Frequency, that's a Greek letter nu, not a letter V, is in cycles per second, or hertz. Let's look at a little math. Lambda times nu, wavelength times frequency, equals the speed of light. Also, we can use a little bit of algebra, and if we're given the frequency, we can find lambda. If we're given the wavelength, we can find frequency. The speed of light is always our constant. Let's look at the units. So meters times 1 over seconds, that's the units of frequency, equals meters per second. You will also see that that divided by seconds as an s to the minus 1. That means we are dividing by seconds. Meters equals meters per second divided by 1 over seconds, and our units of frequency equal meters per second divided by meters. As long as the wavelength is in meters and our frequency in units of 1 over per second, everything is going to work. These equations show that wavelength and frequency are inversely proportional. A large wavelength means a low value for the frequency. High frequency means a short wavelength. You can look at that figure 6.3 again. All of these calculations assume that light is behaving strictly as a wave. But light also acts like a particle. And it's this wave-particle duality that makes light difficult to understand. So Max Planck, he demonstrated back in the early 1900s that light energy existed in specific packets, not a continuum, and he called these light energy packets quanta. The equation he came up with is that the energy of light is this constant denoted by h times light's frequency. Einstein developed the photoelectric effect that light shining on metal kicks off electrons, but only light of a certain energy. Once again, light behaving with discrete energy properties. Finally, Niels Bohr related light emitted by an excited sample of a substance to the electron energy levels. And in the next video, we'll talk more about Niels Bohr. So let's look at homework problem 7 and play around with some of these calculations and these formulas that we've been talking about. So here's the problem. A photon of light is produced by a surgical laser, has an energy of 3.027, 10 to the minus 19 joules. They give us the energy. Now that's a really small amount of energy, but it's also a single photon. So we want to calculate the frequency and the wavelength of this photon. Given the energy, we can calculate the frequency back using the Max Planck formula. There's our formula. Energy equals h, Planck's constant, times the frequency. Now on an assessment, what you probably want to do is write Planck's constant down. I don't know if I remember, I'll put it in the question, but that might be something you want to write on your 3x5 card. So there's our energy equals Planck's constant, and remember nu represents the frequency. The math is very simple and the units work out. Joules will cancel. We'll be left with 1/seconds for our units. We'll just take the energy divided by Planck's constant. Check my math on this. I get 4.568 times 10 to the 14 hertz, or reciprocal seconds. That's an easy equation. Let's look at finding the wavelength. Wavelength is still not too bad. Okay, but we will use the speed of light for that. Once again, the speed of light, a great candidate for writing on your 3x5 card. There's our formula. The wavelength equals the speed of light divided by the frequency, which we calculated in the previous part. We just plug it in. Notice that the units of frequency cancel. We will be left with wavelength in units of meters. Do the math, check me out, please. And hey, let me know if there's a mistake in my slides. This is version 1.0. And I get a frequency of 6.56 times 10 to the minus 7 meters. I think the back of the book expresses that in nanometers. It is 1 times 10 to the 9th nanometers equals 1 meter. Do that conversion, it's equal to 656 nanometers. So low energy light has a low frequency and a long wavelength. High energy photons have a high frequency and a short wavelength. If you have questions, there's my email, don't hesitate. Office hours, Tuesday and Thursday mornings, 9 to 10 a.m. Central Time. And you can also make an appointment if these times don't work for you.